Hello everyone! It is up to the operators engineering and flight operations to determine together what the best operations are for cost savings. Cost savings include not only fuel cost savings but also maintenance costs such as brake costs. As an instructor or a pilot, it is worth understanding the relationship between the procedure you will use for landing and possible carbon degradation due to high temperatures. So the purpose of this presentation is to explain how to adopt fuel economy initiatives that minimize the impact on brake oxidation. All carbon brake manufacturers, all aircraft families, and almost all operators are impacted by brake oxidation. First, we would like to remind you that there are two types of oxidation: catalytic oxidation and thermal oxidation. External contaminants such as de-icing fluids may cause catalytic oxidation. When the brakes have been catalytically oxidized by the contaminant, the thermal oxidation phenomenon occurs more severely. Indeed, thermal oxidation is a natural oxidation process that is due to the porous texture of carbon when the brake is exposed to high temperatures. This phenomenon starts at temperatures as low as 400 degrees Celsius and becomes significant above 600 degrees Celsius. Typically, both thermal and catalytic oxidation affects carbon material properties. Oxidation can decrease the mechanical characteristics such as carbon fiber damage, loss of carbon mass, loss of strength, and ruptures of the carbon brakes. What are the consequences of carbon oxidation? Oxidation affects the braking performance and can even cause loss of braking on ruptured brakes. Oxidation also has an economic impact. An oxidized carbon disc cannot be refurbished. The carbon cannot be reused, and thus it affects the brake life and the brake cost per landing. Before going further into operational recommendations, we first need to focus on the dissipated energy in the brakes. This graph represents the energy distribution among reversers, aerodynamics, and braking. For instance, for the A320 family in autobrake med, the energy absorbed by the brakes is double that of the energy absorbed by brakes when in autobrake low. As a result, the brake temperature will be much higher in autobrake med than in autobrake low. Consequently, the risk of oxidation in autobrake med is higher as well. The analysis was performed on A320 family with associated autobrake mode, but the philosophy is applicable as well to A330, A340, A350 and A380. Now, let's focus only on brake energy and the aircraft landing configuration. In order to prevent thermal oxidation of the carbon, avoid landing techniques that result in repeated excessive brake temperatures. As shown on the previous slide, you can see in the green cells of the table that using autobrake low with reverse max will ensure the lowest energy in the brakes. However, using autobrake med with reverse idle without taking full potential of the reverse leads to very high energy in the brakes, as you can see in the pink and brown cells. From there, the worst configuration would be to use conf 3, that in addition increases the upper speed. This obviously unnecessarily increases the brake temperature and risk of brake oxidation. Therefore, this configuration shown in the brown cell is strongly not recommended. We will present the cost impact of the brown configuration later on in the presentation. As stated in the FCTM, in the Green Operating Procedures chapter, some landing configurations may save fuel. If the performance permits, the best landing configuration to reduce fuel costs and minimize brake oxidation is autobrake low or brake to vacate plus revidal plus conf free. However, if not correctly tuned, these fuel-saving procedures can create significant damage to carbon brakes. If the flight crew needs to reduce the landing distance because of, for instance, the runway length and conditions, aircraft weight or runway exits and occupancy time on the runway, they should adjust the landing configuration. They should prioritize some devices compared to others, in the following order: conf-fuel first, then reverse max, and as a last option, higher auto brake. Do not try to save fuel if performance does not permit it. Auto brake med or 4 or high plus revidal plus conf-free is not recommended. If you use the highest auto brake mode, it should be for performance reasons. In this case, it is better to use conf-fuel and reverse max in order to minimize the amount of energy absorbed by the brakes. We also recommend further actions to minimize brake oxidation. First, the use of auto brake at landing has many advantages: smoother and optimized deceleration that increases the brake temperature to a more acceptable level for taxiing than manual braking. Do not override the auto brake to shorten the landing distance with pedal braking, except in case of emergency. When possible, select the best exit on the runway before landing and find a good compromise to limit energy in the brakes. However, we know that sometimes the flight crew may have a limited choice because of company policy or traffic control order. As described in the standard operating procedures, use brake cooling fans if they are installed to facilitate heat dissipation and brake cooling. These brake fans will lower the time spent at high temperatures and therefore reduce the brake oxidation. Release parking brake at the gate when shocks are in place. If brake temperatures remain high for a long time, the temperature of the critical surrounding structures may reach levels that are not acceptable. Keeping the parking brake on when brake temperature is high can contribute to the dragging brake phenomenon. The dragging brake phenomenon reduces the space between discs and leads to brake temperature rise when aircraft is rolling even without braking. As just presented, we know that some landing configurations can save fuel. However, if not properly applied, some configurations may also be detrimental to the brakes and increase maintenance costs. The first line in green presents an example of the benefits performed thanks to the green operating procedures with reverse idle and conf-free landing configuration. It gives a total of $34,000 of profits per aircraft per year. The second line presents the highest reported brake costs due to brake oxidation when green operating procedures are not properly applied, that is to say, when, for instance, auto brake med is used with revidal and conf-free, or when auto brake is overridden. The cost represents the need to refurbish the brakes before the expected hand life of the brakes. If you apply the green operating procedures, you may save fuel and reduce noise, but the oxidation phenomenon may also be increased, as well as the required cooling time and the runway occupancy time. As a conclusion, remember that all carbon brakes are impacted by oxidation. This is a natural phenomenon. The A320 family is the most impacted aircraft type by the thermal oxidation. Brake costs may cancel fuel-saving benefits if green operating procedures are not properly applied. Brake oxidation can possibly cause unexpected brake rupture and therefore lead to loss of braking on the ruptured brake. As an instructor or pilot, be aware of Airbus recommendations for fuel savings in order to preserve brake integrity and maintain benefits of fuel-saving initiatives. Keep in mind that to prevent unexpected brake damage, you should avoid repeated brake temperature above 400 degrees Celsius, and you should find the best compromise in terms of landing configuration. When performance permits, use auto brake low or brake to vacate plus rev idle plus conf free to save fuel and minimize brake oxidation. However, keep in mind that the use of auto brake med or 4i plus rev idle plus conf free is not recommended. I hope you enjoyed this presentation. See you around for the next one.